Okay, everyone, we get to begin a new unit today. So, polynomials is the next unit that we are going to look at. This is going to seem somewhat familiar because it's very similar to quadratic equations in 20-1. So, let's take a look, first of all, at what we're going to talk about. On this lesson, we're talking about polynomial functions and what is a polynomial function. Okay, so first of all, polynomial function. Now, this is a very complicated way to say it, but essentially, a polynomial function is a function that has terms with the variable of x to the n, where the exponent on n, okay, has to be, do they describe that down here? N, the exponent, has to be a whole number. N is an element of whole numbers. So numbers like 0, 1, 2, 3, etc. Okay, the coefficients, okay, the numbers in front of your terms, have to be real numbers. So really everything's a real number unless we tried to square root a negative. So not much restriction on that one. And then they say an cannot equal 0. So in other words, this leading term, the highest degree on n, has to have a coefficient of some sort. Even if none's written, it's assumed to be 1, right? Okay, so all these numbers in front are called coefficients, okay? The coefficient of the highest power, that's this one here, okay, is called the leading coefficient, all right? And the term independent of x, which means the one that doesn't have x, that's your constant term, okay? And that will just be a number like 5 or negative 22 or something like that. The value of n is the degree of the polynomial. So your highest exponent on your x in any one term is the degree of the polynomial. Okay, let's put this to work and figure out. So we have example 1. Consider the polynomial f of x equals x to the 4 plus 7x cubed minus 8x squared plus 5. State the degree of the polynomial. So the degree, we said, was the highest exponent on a term when we're in this expanded form. So the degree would be 4. The leading coefficient of that term, there's nothing written there, so you assume it to be 1. So the leading coefficient is 1. And the constant term, the term that doesn't have the x, is going to be 5, positive 5. There we go. Okay, recognizing a polynomial function. Expressions containing roots of variables, okay? So if you see a square root over top of the x, okay, then it's not a polynomial function, okay? Or any kind of fraction exponent or a negative exponent, okay? Fraction and roots, they're kind of the same thing. Or the other situation would be as if the coefficient was non-real. The only time that would be happening if you have the square root of negative for a coefficient. So any of those, if you spot them, that would mean it's not a polynomial function. So let's take a look at example 2 and see which ones of these are and which are not polynomial functions. Okay, so part A, we have x cubed, that's fine. Fraction exponent, because of that, not a polynomial function. Okay, part B. So we've got 2x squared minus 7x to the negative 1. Can't have a negative, so not, therefore not a polynomial. Probably should put therefore. Okay, so fraction exponent. I should probably write the reason why. Fraction exponent, therefore not a polynomial function. And this one is negative exponent, therefore not a polynomial function. All right, next one, let's take a look at that. X to the 4, 9,029x cubed, negative, and then root 17 of x squared plus, okay, the numbers are bizarre, but the exponents on x seem okay. The coefficients, we're not square rooting a negative, right? This is the root of positive 17. So this would be a polynomial function. All right, next one. Square root of 5x cubed. Now that x cubed, because the root goes over top of that x, guess what? That's the same as saying x to the 3 halves. So because of that, fraction exponent. Okay, fraction exponent, therefore not a polynomial. Okay, if you guys want to try the next two on your own, pause the video. Okay, let's look at this one. You would have thought that this would have been not a polynomial function, but x squared and then it's a square root, so divided by 2. So that means that's really just x to the 1. So that one's actually okay. This one is a polynomial function. And this last one, right here, the exponents on x are okay, right? 3 and 1. But right here, we're square rooting a negative. That's not a real number. So therefore, not a polynomial function. All right, good job. Let's take a look at the next page. All right, so we're going to look at degree, leading coefficient, and constant term again, but apparently a polynomial can be in a disguised form, so not what we saw the last time. But this first one, let's take a look at that. This one actually looks okay, right? Except for one thing. Your leading term, or your leading coefficient, is not necessarily the first term. You look for the highest exponent on x. Right here. That there tells you not only the degree is 3, but the leading coefficient is the coefficient in front of that, so negative 25. Okay, your constant term, negative 39, the term without x. Okay, now be a little bit tricky. Take a look at that. What looks different? We have basically a binomial times a binomial. Well, guess what? That is really not in the right form for us. We need to expand it to determine degree, leading coefficient. So if we expand that, we'll get 10x squared, and then plus 35x minus 2x, so plus 33x, and then minus 7. Okay, now you guys go ahead, pause the video, and fill in the degree, the leading coefficient, and the constant term. Okay, so we should have gotten a degree of 2, that's our highest exponent, the leading coefficient, the coefficient in front of that highest exponent, and then our constant term would be negative 7. All right, did you guys get that? Awesome. Okay, example number 4. In the following polynomial functions, determine the degree, the leading coefficient, the constant term without expanding. And then verify the results in I by expanding, which is a bit of work, and simplifying the polynomial. So without expanding, let's see. So that 2 is not going to contribute to the degree. If we expanded 3x minus 1 squared, really the 3x would end up being squared, right? So that would be like 9x squared. Okay, and then we have this term, which would then also be multiplied. That would contribute to the highest exponent. So we'd have 5x squared and a 2, which would help our leading coefficient, and then 5 and 9x squared as well. If you multiply all of those together, you get 45, 90x to the 4. So I took the highest degree in each factor. This one needed to be squared, and then times 2, and that means our degree is 4, our leading coefficient 90, our constant term, now that's a little bit trickier. We have to once again take this 2, negative 1, and we're squaring it, so positive 1. I could show being squared. And then times this constant term, so times 1. So it's 2 times negative 1 squared times 1 is going to be equal to 2. And there's our constant term. Kind of a sneaky way to get around expanding it. Okay, now to expand that, it's a bit of work. 3x minus 1 times 3x minus 1 squared times 5x squared minus x plus 1. Okay. Oh, this one's not squared because I wrote it twice. Okay, so why don't you guys go ahead and expand that? I will as well, and we'll compare to what our answers were. Okay, pause the video. Whew, that was a lot of work. Holy cow. Hopefully I didn't make a mistake in here. Did we get the same answer? Hopefully we did. But one thing for sure, we confirmed what we guessed, or calculated, I guess, from up above. Our degree was 4, highest exponent on x. Our leading coefficient, the coefficient of that term, is 90, and our constant term turned out to be 2. Awesome. Okay, I want you guys to take a stab at B and see what you get for degree and leading coefficient and constant term. Please note, slightly different than the one we just did. There's a plus sign here. Okay, so if you feel like you want to multiply that out, this one's not too much work and not as much as the last one. But try and do it without multiplying out first and then check it with the multiplying. Okay, So pause your video. I'm going to do the whole thing on B, and then we'll check our answers, see if we got the same thing. All right, so to get our degree, I kind of took the highest degree, squared it, still have the 2 out front, plus, and took again the highest degree from this factor, then simplified a bit, 2 times 9, 18x squared, plus this time 5x squared to give me 23x squared. Degree 2, therefore, leading coefficient 23, and the constant term, same idea, take the constant part here, -1, square it, times 2, I should probably show that. Okay, and then plus in the constant term here would just be 1, so plus 1, and we get a value of 3. And there we go. If we expand it, it confirms it as well. Okay, hopefully you guys got that one as well. Okay, let's look at example 5. Consider the polynomial function p of x equals 7. Okay. Explain why the polynomial function p of x equals 7 has a degree of 0. Okay, so degree is our highest exponent on x. And there is no x, is there? Okay. If we pretended for a minute that there was one, I would have to put what exponent on that x so that it actually wouldn't be there. And that would be a 0. Because guess what? X to the 0 is equal to 1. And 7 times 1, still 7. So it is degree 0, okay? Explain why this type of function is called a constant function, okay? So if you were to graph p of x equals 7, you would actually get a horizontal line at y equals 7. And guess what? No matter what value of x on that line, the y value stays constant at 7. And that's why it's called a constant function, because the y value stays constant, stays a constant value of 7. And I'll just put in brackets, no matter what x is. Okay, that's the idea on that one. Great, let's look at the next page. Okay, so classifying polynomial functions, basically this is what we call polynomial functions. And many of these you've already heard. We've heard the term mononomial, okay? That actually means a one-term polynomial. Or binomial means a two-term polynomial. Trinomial, 3 terms in the polynomial. And then if you have 4 or more terms, they don't usually name those, although you could call 4 terms quartic, but typically they just go with a general term of polynomial after that. All right, you can also classify polynomial functions by degree. So if you hear something like it's a quadratic, that means our degree is 2. If it's, there's quartic, sorry. Cubic is degree 3. Quartic, degree 4. Okay, and we just talked about an example where it was a degree 0, and that was called a constant function, and degree 1 is called a linear function. Okay, so we kind of need to know those ones. Okay, let's complete the chart to just reinforce that. So if we have p of x equals c, notice there's no x, so it's like x to the 0. Remember that was degree 0, and it was called a constant function. Okay, so you get the idea. Why don't you run through and write down what each of the degrees would be and what type or what name of the function it would be. Okay, we could probably also, yeah, no, this is fine. Okay, because we're just based on degree here. Okay, so fill in that chart and pause the video. We'll check back in a minute. Okay, so hopefully you arrived at the same thing I did, just using the information given in the paragraph above. And yes, you do need to know what each of these are, okay? We're not going to research the names for degrees 5 through 10. Feel free to do that in your spare time, you know, Friday night when you have nothing else to do. Okay, now we can also classify by type of coefficients. So if you hear that a polynomial function is an integral polynomial function, you'll hear that quite often. That's referring to the type of coefficients. What it means is the coefficients, even the constant term, are integers. So the coefficients are integers, hence the name integral, okay? Or rational. Rational, the word rational means fraction, right? Or something can be expressed as a ratio of something over something. And take a look, because of this coefficient, we would then classify that as a rational polynomial function. So coefficients, so how to write this here would be the coefficients are elements of the integers, okay, whatever you want to call the coefficients. Here the coefficients are rational numbers.